All right, there was one request for a problem to be worked out this week. It was question 4 on web work. And the request mentioned having trouble with the trig in a reduction of order problem, so I figured it's this from review 2. And we're just gonna work through it. It's weird that the second equation doesn't match the first, but I think that's probably just a typo. So I'm going to work through the problem as given. I'm just copying it down on my tablet before I get started. E to x sine 4x. Okay, y1 is e to x sine 4x, y double prime minus 2y prime plus 17y equal to 0. Okay, so here's the problem that we have, and it's a reduction of order problem. We know that because y1 is given and we're trying to find y2. Just as a reminder, the calculus and algebra you can expect on the exam will be much simpler than what you see on WebWork. The examples that I linked on the homepage of Blackboard are a bit more appropriate. Just WebWork is a tool to practice. So if all the trig and stuff is bothering you here, don't worry. It's probably a lot harder than our exam. I haven't actually worked this out yet, but I'm guessing it is. So when we have a reduction of order problem, we start by assuming that y2 is going to be given by some unknown function u times y1. And the entire process is just to try and find that u. So for us, it's going to be u times e to x sine 4x. And in order to find out what u is, we're going to plug y2 into the differential equation and find conditions for u that'll make the whole thing satisfy our ODE. Because I want to plug it in, I'm going to need the derivatives. So I'm going to have to use product rule all the time when I have these reduction of order problems because u is a function of x. So I need to account for its derivative when I'm taking the derivative of y2. So I might take derivative of u, have u prime, and then leave the second part, e to x sine 4x, the same. Or I might leave u as it is, and then take the derivative of that second part, e to x sine 4x. This itself is also a product of two functions, so I'm going to have to do a product rule here as well. First, I'm going to take the derivative of e to x, but that's just e to x, and then leave sine 4x as it is. And then I'm going to take derivative of sine 4x and leave e to x as it is. And the derivative of sine is cosine, no negative. So it's just going to be cosine 4x, and then I multiply by 4 out front because of a chain rule on sine cosine. So that's my first derivative, and then I'm going to have to do this again. I'm going to leave it in the form it is. Sometimes when we do the variation of parameters functions, I like to reorder everything, but rearranging the u's might cause more confusion than help. So next I'm going to take derivative of this first term here. So if I take the derivative of u prime, it becomes u double prime, and I leave e to x sine 4x the same. Or I might leave u prime as it is, and then take the derivative of e to x sine 4x. But that's going to be the exact same thing that I got when I took the derivative of e to x sine 4x above. So I'm just going to go ahead and copy that down here. And now I'm going to try to take the derivative of this whole second term, u times the term in brackets. And so first, if I take the derivative of u, I get u prime, and then I could leave everything in brackets as it currently is. So e to x sine 4x plus 4 e to x cosine 4x. And real quick, I want to point out one way that you can know that you're on the right track with these product rules. In the reduction of order problems, you're always going to have these two terms that match from taking the derivative of the first and second parts of your product rule from y2 prime. So these middle terms are always going to be the same, and you'll get 2 times whatever this derivative was. And then I'm going to leave u as it is and take the derivative of everything inside. And I'm probably going to need more room than I have right there, so I'm actually going to just write it here like this. So it's going to be u times the derivative of e to x sine 4x and 4e to x cosine 4x. I already know the derivative of e to x sine 4x. It's the term in brackets, so I'll write that down first. So that's just me trying to take derivative of this part. And then I'm going to go ahead and take derivative of the second part. So it's going to be plus 4, and then let's say I took my derivative of e to x, so cosine 4x stays the same. Or I leave e to x as it is, and then take the derivative of cosine 4x. Derivative of cosine is minus sine. And then I multiply by 4 out front because there's a 4 inside the sine cosine. And that's my second derivative. It's a mess, but I'm going to leave it the way it is for now. Because it has, well, I'm going to make one change. I'm going to simplify that these two terms added together is just 2 times that term. Instead of writing all this out again, I'm just going to make that change. So I'm just adding those 2 terms together, and when you add 2 things, it becomes 2 times whatever the thing was. That way it's a little bit smaller for when I start. Oh no, I only grabbed part of my function. I better get the rest of that in a second. Okay, there we go. So that's all my derivatives, and now I want to plug all this into my ODE and try to figure out what u has to be in order for the ODE to be satisfied. So I'm just going to start plugging in all my derivatives into this equation for my ODE. So I'm going to start with y2 double prime. So it's going to be u double prime e to x sine 4x plus u prime times 2 e to x sine 4x plus 2 times 4 is going to be 8 e to x cosine 4x. I'm just multiplying that 2 through because I want to have u prime out front so that I can start simplifying my terms in a minute. And I'm going to simplify this term right here before I plug it in. I've got e to x sine 4x minus 4 times 4 e to x sine 4x. So that's going to be minus 15 e to x sine 4x. Because 4 times minus 4 is minus 16. So I've just got 1 minus 16 is minus 15. And then I have this 4 e to x cosine 4x out front, and then 4 times e to x cosine 4x. So when I add those together, it's just going to be plus 8 e to x cosine 4x. And I think I can fit that all. I'm going to try my best. So u times minus 15 e to x sine 4x plus 8 e to x cosine 4x. Okay, it really doesn't fit, but that's okay. And then that was just adding my y prime out front. Now I'm going to subtract 2 times y prime. So it's going to be minus 2 times this term right here, the y2 prime. And I would always recommend writing it out and then simplifying, but if I do that, you all aren't going to be able to see all the functions on the same page. So I'm going to go ahead and multiply through my minus 2 as I go. So I've got minus 2 u prime e to x sine 4x, and then minus 2 times u times e to x sine 4x plus 4 e to x cosine 4x. And then thinking about multiplying that minus 2 all the way through, it's actually going to be minus 2 times e to x sine 4x minus 8. Ooh, minus 8 times e to x 4x. So I just distributed that minus 2 inside, again, because I know I'm going to be combining all my u's, u primes, and u double primes, so I want to see those things written together to easily add them. I could do the same thing here, although it tends to bother us a little bit less. But my minus 2 could be written like that. And I want you to note that eventually I'm going to be adding all my terms together by what kind of u or derivative they are. So I'm going to add the top u and the middle u, and then there's going to be one more u at the bottom when I do my 17y. And those u's are supposed to cancel out, so hopefully we'll be seeing that everything on this right side of the screen starts to simplify. My last term is just this plus 17y, so all I'm going to do is take 17 and multiply it by the original guess for y2 I had. So it's going to be plus 17u e to x sine 4x, or emphasizing that u is out front, I could just see it like this. So with these reduction of order problems, at this point I should expect, if I did everything right, all of these u terms over here should simplify to 0. So let's see if that happens. Oh, I forgot to write my 17 somehow. There. So first I'm going to check my e to x cosine terms. I've got plus 8 e to x cosine 4x here, and minus 8 e to x cosine 4x there, and then no more e times cosines. So those are going to cancel out to 0. And then I've got minus 15 e to x sine 4x, minus 2 e to x sine 4x, so that takes me to minus 17 e to x sine 4x. But then I have plus 17 e to x sine 4x down bottom, so all three of these are going to simplify to 0 as well. So in the end, what I'm going to be left with is 0 is equal to u double prime e to x sine 4x plus u prime, and then I'm going to just add everything in these terms together because they all belong to u prime. So I've got 2 e to x sine 4x here, and then minus 2 e to x sine 4x there. So those two are going to cancel out. Oops, to 0, because 2 minus 2 is 0. And all I'm going to be left with is actually going to be that 8 e to x cosine 4x. And then one last thing I'm going to do to try and make like everything a little bit easier on me in the end is I'm going to note that there's an e in both my terms, and this is equal to 0, so I can multiply or divide the whole equation by anything I want and it'll still be equal to 0. In this case, I divide through by those e to x terms, just cancel them out, and I'm left with u double prime sine 4x plus 8u prime cosine 4x. And this is the step where we introduce the reduction of order, which I'm going to just move to the next page. So I'm at 0 equals u double prime, I think sine 4x plus 8u prime cosine 4x. Let's just make sure that's true. Sine plus 8 cosine. Yep. Okay, so now is the part that we do to turn this into a first order equation so that it's something that we already know how to solve. That means I'm going to say I'm going to take w to be u prime, which means w prime is u double prime. And I can rewrite this equation as w prime sine 4x plus 8w cosine 4x. This is going to be really gross. So I'm going to solve it as a separable equation. So I'm going to be trying to move all the w's to one side and x's to the other. So I'll be left with dw over w is equal to minus 8 times cosine 4x, divided by sine 4x dx. And then I'm going to have to integrate both sides. U sub will get me through the integral on the right side. The left side just becomes natural log w. And then for the right side, I don't want to use u because that's going to be confusing with it having come from above, so I guess I'll do v, but this is like u substitution. If I make v equal to sine x, then dv is the derivative of sine, which is just regular cosine, x dx. But I want to be getting rid of sine 4x and cosine 4x, so I just have to remember to multiply out front by 4, and then I should be good. What this means is that dv over 4 is the same as cosine 4x dx, and v is the same as sine 4x. So this top part, cosine 4x dx, just becomes dv over 4, and this bottom part becomes sine 4x. Sorry, no, that would be no good, right? It becomes v. Forgot to make that substitution. And then minus 8 over 4 is going to be minus 2, so this is just minus 2, the integral of dv over v, or minus 2 natural log v. And then the rule with natural logs is that some constant times a natural log is natural log of the argument raised to that power constant. So this is natural log of v to minus 2. And the reason I want to do that is so that I can cancel out the natural logs on both sides eventually. I have to remember to replace my v, so that was sine 4x to minus 2. Oh, and I'm sorry, I dropped my minus 2 out front. No, I didn't. I brought it inside. Okay, cool. So then all that's equal to natural log w. So I've got natural log w is equal to natural log of sine 4x to minus 2. Where the sine 4x is the whole thing raised, not just the x. Now I take like e to power both sides to cancel out the natural log, and I'm just left with w is sine 4x to the power of minus 2. I'm going to have to think about how I'll integrate that, but we'll address that when we get to it, I guess. Then at this point, I remember that I started this whole problem by saying, I think y2 is u times y1, but I don't know what u is. Now I've solved for w, and I just want to like go backwards in the process to recover u from that. So since w is equal to u prime, that means that u is the integral of w with respect to x. Because I could integrate both sides to get rid of the sine, or the prime on the right side. So, given my w from before, that means that u is the integral of sine 4x to the power of minus 2 dx. How do I do this? I'm pretty sure that's just one of the weird trig functions, so let's Google it. integral 1 over sine squared. Oh, I wonder if it's on our, let's check our formula sheet first. Maybe it's there. No, because I don't hate you all. I would not ask you to integrate this thing. Okay, so I got a 1 over sine squared. I'm just pulling up an integration table on my phone. Back to the screen. The integral of 1 over sine squared. Just one simple integral table is all I need. They're all like screenshots of people's YouTubes. Oh, okay, it's just negative cotangent. Interesting. So integral of 1 over sine squared is negative cotangent of x. I'm going to move to the next page to just do the thing that we actually need. 1 over sine squared of 4x dx, knowing that integral of 1 over sine squared of regular x is negative cotangent of x, which is like 1 over tangent. We'll deal with that once we simplify everything. So in this case, I'm going to do another v sub. V is 4x, so dv is 4 dx, or dx is just dv over 4. So u is going to be the integral of 1/4 1 over sine squared v dv. The constant out front isn't actually going to matter for this because we end up using it to build like a fundamental solution, but just to be careful for how we'd normally integrate things. So this would be 1/4 negative cotangent of v, but v was just 4x, so it'd be like that. And then cotangent, I'm pretty sure, is just 1 over tangent. I want to make sure that's right before I proceed. Yes, cotangent is 1 over tangent. It's not one of the hyperbolic or whatever. So since tangent is sine over cosine, this is just going to be the opposite. It's negative 1 over 4 cosine over sine. Okay, and that's looking promising because I know that, oh, I can't click on this. I know that I started with y1 e to x sine 4x, so from what we know of later sections, the other solution is supposed to be e to x cosine 4x. So seeing something where I'm going to multiply a cosine and divide a sine is promising. I originally said that y2 is u times y1, and that's the thing I'm trying to find, where y1 is e to x sine 4x. So once I find my u, I still want to figure out what is my y2. So y2 was u times y1, and y1 was e to x sine 4x. So it's going to be minus 1/4 cosine 4x over sine 4x, where y1 is e to x sine 4x. So then this multiply divide by sine is going to cancel out, and I'm just left with minus 1/4 cosine 4x times e to x. And constants don't matter when I'm finding fundamental solutions because I always multiply by like C1, C2 in my final answer. So I could just say that y2 is e to x cosine 4x. And my general solution would be y is C1 e to x cosine 4x plus C2 e to x sine 4x. I did swap the numbering on you here. This is y1 and this is y2, but the order doesn't matter. So let's make sure I got that right. Here I just put my y2, so e to x cosine 4x. And here I do the two things. I better make sure to preserve their order here. So y1 was sine 4x. Okay. And that's right. So we finished the problem. Almost all of this problem is not the kind of thing that you would need to know on the exam. So let's just roll back through it, thinking about this being a problem that this type might be on the exam tomorrow. I care that you know how to do this, taking your derivatives using the product rule. I think that taking a product rule with another product rule inside is quite a mess, and it would be complicated and difficult in a short exam, so you could assume that's not going to happen. But then, assuming you got your derivatives, you should be comfortable with the idea that you're going to plug into your ODE and you're going to try to cancel out your u terms, and then simplify your equation as much as possible with the understanding that you're going to be trying to solve a first order equation afterwards. So you should be comfortable with this reduction of order step. It's kind of the crux of the method. And plugging it in and then identifying that now it's the type of equation that you could try to solve using whatever method you prefer from exam 1. But once you get to this point, again, we're doing things that wouldn't really be fair game on an exam. That's a complicated integral. Like it's just u sub, but u sub of trig functions is very easy to mess up, especially if you're stressed out taking an exam. And then you should recognize the undoing step, where now you have to integrate w to get u back, because eventually you want to find the answer y2 that has u in it. So you should get to the point of trying to integrate w, but this integral I had to look up in an integral table, and your integral table for the exam doesn't have it, so you could assume that you don't need to know how to do that. But whatever easier integral you have, be comfortable with taking u and finding it through that integral. And then once you have it, remember that you do have to plug back in multiplying by y1. And here we've kind of returned to things that would be fair game for the exam. You figure out whatever y2 is once you plug everything in. And then remember that in order to build a general solution, you do C1 times one solution plus C2 times another. So as long as you're okay with those big picture things, I would not worry about all the trig that was happening in this video. Good luck everyone who's studying tonight. Please sleep. Don't rush to cram things in. Remember, we have makeups for our exam problems, so it's better that you come in fresh and are able to do really well on the problems that you really know, instead of trying to cram in knowing one extra topic. Maybe just say that you're not going to do that topic on the exam and save it for the makeup. That way it's more manageable when it comes time to do the makeup, instead of having a bunch of little mistakes scattered about. So I'll see you all tomorrow. Best of luck.